Hello, so here we will be discussing chapter 17, regression on last main topic. And the chapter opens with a question about human population genetics, recent human evolution. But we know humans have dispersed. I guess you have already heard humans have dispersed in different regions of the world over the last 100,000 years, approximately. And we know this based on the archaeological record, but also based on genetic data, where people have realized over the last 10, 15 years that if you go further away from Africa, genome-wide genetic variation tends to decrease. So here you see this relationship on the x-axis, distance from East Africa, and on the y-axis, genetic diversity within different human populations, each represented by a point here, and which basically follows the pattern here, as you might observe, approximately. And this type of relationship, it can be described as a regression curve, which could allow, for instance, us to predict how much diversity we would expect for a population on average 15,000 kilometers living today, 15,000 kilometers away from East Africa. Yeah, the regression is the method, is a tool to make this prediction, to predict diversity, to predict response values given values of an exponential variable. So the tool that is regression, it's a function, it's a mathematical function that describes the relationship between two numeric variables, as we said, and we use it for prediction. The variables have a special relationship between them. One is the response. We have general one response, or also called the dependent variable, and we have at least one, but potentially also more exponential variables, also called independent variables. So philosophically, we would expect this type of relationship to be able to use this function for prediction. Yeah, so correlation we had learned last week, and regression analysis is closely related to correlation. Again, both are the simplest version of regression, linear regression, with a single exponential variable is uses data of the same type that we learned we could use with to do correlation analysis, but the goals of the two analyses are somewhat different. In correlation, we just study the strength of relationship between any two numeric variables, whereas in regression, we construct a function that allows also prediction. And the function will have a slope and intercept. So how the two type of analyses relate to each other, we can also see from in these three examples. So just try to imagine how the correlation coefficient will be in the across the three pairs of data sets. So here you should be able to see that the correlation coefficient should be 1, right? But it should be positive and 1 because the values on one variable can be perfectly predicted by the values of the other variable and vice versa. That means correlation coefficient of 1, and that these should be here correlation coefficient should be positive, but something less than 1, because given the variation in one type of data versus other type of data. How about the regression lines? in fact, the regression line here and the regression line here, as you see, they are basically the same. They have the same intercept, the same slope, whereas regression line here is different. In fact, this was something I took from the book. So these two have the same slope, as you see. So here R indicates the correlation coefficients, and the second part is the regression, describes the regression slope, and it's the same regression line, as you see. Slope is the same, but here the slope is twice as much as more than twice as much as the previous one, and you can see it's steeper, so slope is higher, whereas the correlation coefficients are the same, because the correlation coefficient is a measure of coupling between the two variables, and the amount of coupling relative to overall variation, the two variables it turns out to be the same between this one and this one. Yeah, correlation doesn't assume explanatory response relationship. There's no hierarchy among between two variables. It only describes strength of relationship, the strength of coupling. Whereas regression is a tool for prediction. It's actually one of the simplest ways of machine learning. You could also say automatic prediction based on data, a tool to make a prediction. And it comes in different types. The main type we will be learning today is linear regression, but we'll also briefly touch upon non-linear regression types. And what distinguishes linear versus non-linear is basically whether the relationship between the experimental and response variables are linear or not, whether they can be described here as a line, as in these cases. Whereas this, what would be non-linear, a curve would be non-linear. You could also have simple linear regression with a single explanatory variable versus multiple regression with multiple explanatory variables, which could also be linear or non-linear. Multiple regression, the distinction of multiple regression is that you have multiple explanatory variables and a single response. And logistic regression is a special type of regression in that the explanatory variable is numeric, but the response is binary. Response is 1-0 type. And we'll also briefly learn about that at the very end. Okay, linear regression. It is a tool to describe linear relationships between a response and an explanatory variable, as we said, and it assumes that the relationships are linear, as the name implies, and also that values of y, the response, are normally distributed for each x value with the same variance. So this is a description of that relationship. So for each x, we assume there's a population of y that are normally distributed with the same variance for each x. Okay, that's one other assumption, that each value we observe, each y value we observe is a random sampling corresponding to a specific x value. But x, the values on the x aren't necessarily supposed to be random. So we might have collected x regularly, or in a fashion that doesn't necessarily represent random sampling. Whereas the values on the y, the response we expect, are random results of random sampling. And also, we'll come to that later. X values we assume are perfectly measured, but y might have noise. So we assume there's no noise on the x, there's noise in the response. I mean, based on these assumptions, we'll be learning how to construct this line and how to describe the function that relates x and y. And we'll also learn how to calculate our trust confidence in this function. Yeah, the function has 4 components. 2 other variables we're studying, x and y. Y is response again. X is the exponential variable, values of the exponential variable. You can think of these as 2 vectors. Y is a set of values, x is a set of values. Alpha and beta, these are single values. Okay, these are parameters of the model that we will be predicting, and that will be describing the relationship between x and y. Alpha is also called the intercept, and beta is the slope of the regression line. Beta, the slope, alpha, intercept. And again, y and x are sets of values that are matched. These are vectors in reality, and these are single values, the parameters. So for a population, we talk about alpha and beta for regression formula. From a sample, what we calculate are called A and B. We distinguish again between the relationship between x and y at the population level versus at the sample level, because populations, samples from the same population, multiple samples from same population, can give slightly different, we can construct slightly different regression models. We can estimate slightly different intercept and slope values for different samples. So this is this difference in notation, alpha versus A, beta versus B. The difference in notation aims to emphasize that these are estimates we calculate based on samples, and with another sample they might change. Okay, so let's try do some small exercise, thought exercise, to try to guess what alpha and beta would be in these different regression examples, to see that we develop a feeling of the regression formula. So here we have a positive relationship, positive correlation coefficient, of course, and the slope should be a positive value, right? Whereas here, if the relationship is negative, if the correlation coefficient is negative, the slope will also be negative. If correlation is negative, slope will also be negative. Correlation is positive, slope will also be positive. Here, slope should be 0. If correlation is 0, slope is also 0. And there the relationship is very clear. And here we're comparing 2 regression lines with positive slope, and their slopes are the same, but the difference is in the intercept. So this one has high intercept, this one low intercept, right? Okay, so all of us should be able to interpret the slope and the intercept across these lines. Okay. Yeah, so the coefficients values qualitatively you should be able to define. But of course, we don't just want to make qualitative inferences. We want to calculate the formula itself. And how to calculate the formula? Well, we have to find the way to find a best fit line to the point. And one with a commonly used approach there to find the best fit line is to define best as the line which introduces the least squared differences between each data point in our data set and the line. the vertical distances to the line. You could define other criteria for best, but this in general works pretty good. And this is called least squares regression. The least squares comes from the fact that we calculate the line itself that we learn to calculate is the line which minimizes the sum of squared distances here. Okay, sum of squared distances is minimized. Yeah, so let's take this example from the book. We have a data set, these red points, and we can add different types of regression line on this to the data. Let's see how the residuals would behave. If we add this regression line, we would have quite large residuals, as you see. If we tilted the line a bit, we would still have pretty large residuals. If we tilted it further a bit more, at this point, the deviations, the residuals, squared values of the residuals, are smallest, become smallest. Okay, so we want to find this line. You understand the logic, I hope. The line that minimizes the squared residuals. And residual is the distance between each point and the line, the vertical distance between each point and the line. Okay, and squaring, of course, if we just summed up the residuals here, sum the residual values, we would obtain 0. But squared residuals, it's like variance, and it is always a positive number. Okay, so how to get this line? Well, we need an estimate for the slope and an estimate for the intercept. And the slope estimate goes as follows. Here is the slope estimate. It's the sum of products, just like we had in the correlation coefficient. As you might remember, correlation coefficient, we had sum of products in the numerator and the product of sum of squares of x and y in the denominator, but with the square root. Here it's slightly different in that in the denominator we don't have y, we just have x. So we are dividing the sum of products, the difference between each x value, the mean of x, each y value with the mean of y. This we calculate for each I, for each observation in our data set, and calculates the differences, the product of the differences, and sum of the products. And in the denominator, we have the difference, the sum of squares for x, that is the difference between each x value and the mean of x squared. Okay, and that is the slope estimate. So there is by theory, people have shown that this slope will give the smallest deviations, will minimize the square differences. And yeah, this is an old result. And yeah, just a reminder, the sum of products term, if you divide that by n-1, that's called covariance. Just like when we divided the sum of squares by n-1, we got the variance. When we divide the sum of products by n-1, we get the covariance. And the estimate for the slope, B, is basically covariance divided by variance of x, because if you divide both this term and this term by n-1, this becomes covariance, this becomes variance. So basically, the same thing. You don't have to memorize the covariance formula, but it's good that you've heard the term. Again, if you end up continuing doing computational biology, biostatistics, bioinformatics, then these will be terms that you will have to deal with. And also genetics, transmission genetics. Okay, so yeah, the slope estimate is the covariance divided by variance, we said, and correlation coefficient is the covariance divided by the product of two standard deviations. They're both the same. Okay, coming back to the question about regression, constructing the regression formula. Well, we got an estimate of the slope, and now we also need to get an estimate of the intercept. And how can we do that? Well, the least-squares line, it by theory has to pass through the mean of x and the mean of y. So if we know the slope, and if we know the mean of y and mean of x, of course we do, calculating a is trivial, right? Calculating intercept is trivial. Just calculate, you have the means, you have the slope. A is basically mean of y minus this product. And thus you can get an estimate for the least square regression curve. And we already saw this relationship. Okay, and here we have an example in the book. It's a regression example where people had observed that as male lions get older, their nose goes from pink to black, and the older the lion, the blacker the nose. And so based on this, the question is, can we predict the age of a lion? Given a set of data where we know both the age of a lion and also how black its nose is, can we construct a reliable regression function that would allow us to predict the age of a lion, which we could measure the nose blackness of, but we don't know the real age of. Okay, can we use this as a prediction tool? The example is slightly off because in reality, the biological relationship is such that by age, some phenotypic change happens, right? So at the biological level, the relationship should be age would be the experimental variable, proportion black, amount of black nose would be the response variable. But here we're trying to reverse the relationship and use the proportion black to estimate age. So it's not exactly fitting the assumptions we made, where we were assuming X values are perfectly measured, but Y may have noise and so on. For each X, we have a random sample for Y, etc. So these would have applied if we had age as explanatory, Y as, we had age as explanatory variable and proportion black as response. But our question is different. Our real life question is, can we predict the age of a lion using how black its nose is? And so we are using we're turning the tool upside down, and we'll be trying to use it in a way which is not very conventional, and in fact doesn't totally fit the assumptions. But anyway, let's continue. And in real life, we also sometimes encountered similar problems that doesn't exactly fit the philosophy. Okay, but yeah, we have to be aware of, and perhaps consult a statistician if you were really to solve this problem, and you should, for one thing, notice that the problem isn't exactly fitting what was described to apply to this tool. That is regression. Some assumptions seem to be weak and not fulfilled. And then what you could do could be to consult a statistician to decide on what would be the best. But anyway, let's, for sake of simplicity here, ignore that small issue, and let's try to construct a regression curve where we would be able to estimate the age of a lion, where of which the nose is 50% black. Okay. Yeah, we already discussed this. Response, if this is our question, of course, the response would be age, and the exponential variable would be percent black nose, proportion black. This exponentially, this is response. Yeah, so this is data. Seems like there's a positive relationship, as you see. And we want to construct a regression line, the least squares regression that minimizes the squared residuals, sum of squared residuals, as you remember. Okay, how can we calculate the regression line? We need a set of statistics. We need the mean of x and y. We need the sum of products. We need the sum of squares of x. We then can calculate the slope, and then we can calculate the intercept. So 5 sets of values. Okay, and here we have the means of x and y. We have the sum of squares for x, sum of squares for y. What sum of squares means, please don't confuse, it's the sum of the squared differences between each value in a data set and its mean squared. So we have x and y, and we have the, what's this? The sum of products, right? X differences times y differences. Again, here, x and y are vectors. X bar and y bar, the mean of x and y, these are single values. We subtract a single value from a vector, we again get a vector of differences, multiplied, then summed up. Okay, and what's the slope? It's the sum of products divided by the sum of squares for x, right? Sum of products, sum of squares for x, divide one by the other, and you get a slope of 10. Good, and then what's the next step to calculate the intercept? We said the regression line will pass through the mean of x and mean of y. So we already know the mean of x and mean of y. We know we've calculated the slope. So thus we can get the intercept here. And this is our regression function. So each unit of increasing proportion black will also lead to increasing age. That's what the formula implies. Of course, in reality, the biological relationship is the other way around. Yeah, and we can also see that there's a positive relationship, right? As proportion black increases, age increases. And this is the curve there. How could you draw this by line if you have this regression curve already calculated? You could draw 2 points. Sorry. You could calculate the estimated values for x and y for two values of x. Let's say the value of y for x at point 2 and the value of y for x at point 8. You have 2 points, and then you could have just drawn a line. Yeah, and now the line is the predictor, right? It tells us the predicted values of y for each value of each corresponding value of x. So the age of a lion with the predicted age of a lion with the proportion of its nose 50% black would be something like the drawing a line here, then going to left-hand side and finding the value that cuts the y-axis. So the finding the value in y that cuts the axis when proportional black would be 0 right here. So going up and then going to the left. And it should be something like 7-ish, we can guess. But of course, calculating this would be much nicer. By hand, we would insert here our x value, 50, and 0.5. There's a proportion 0.5 plus something. Yeah, you will get something like 6, 7-ish. 6.2. Okay. So this was prediction, but now we'll start discussing something else, which is confidence. How much can we trust the slope, and how much can we trust the predicted values? We made a prediction, but is it really reliable? And we'll also briefly talk about how much can we trust values predicted outside the range of the original date. That's called extrapolation. So is it okay to extrapolate? That'll be something else to discuss. How much the points fit the line, that reflects our confidence in the slope. If there is a lot of, if the fit is well, then we will be more confident about the slope. If the fit is weak, we will be less confident. And the fit is basically measured by what we were trying to minimize, the residuals. That is the difference between predicted values and the observed values. And predicted values in statistics are shown by this hat symbol. So y hat means the predicted value of y given a regression formula. So y minus y hat is the description of residuals. Y are the real values, y hat are the predicted values. The smaller these values are in absolute terms, smaller they are, the better the fit and more confidence we'll have in the slope. And this difference, the size of the residuals, we will be using to calculate our confidence in the slope. This is another representation of the same thing. So we have 4 points where we've collected data for the corresponding x values, x1 and y1. This is the first observation. And this is the regression line. And this is the predicted value, y1 hat. So the residual here is this difference. And here we have, the residual is negative. Residual is calculated as observed data minus the expected data, predicted data. Here, the y1 value is lower than the predicted value, so this is a negative residual. This is a positive residual, y2 hat, right? Of course, the hat, these predicted values, we can only calculate after having calculated the regression line. Okay, so the residuals are y minus y hat values, which are different for each data point. Yeah, the residual for the 31st lion, last individual in the data set, which has a proportion black 0.79 and its age is 8.8, is here. It's actually pretty close to the regression line, as we see. So its residual will be small and it will be negative. And this guy, it will have a large and positive regression residual. Yeah, so to calculate the residual for that individual, sorry, 31st individual, we would be calculating the estimated value based on the regression line here, which is y hat of the 31st lion, our regression formula, and as input the proportion black of the last line, 9.3, and the difference between the observed value and the predicted value is the residual. This is the value here. And okay, so this is the residual, and we said the lower the residuals, the more confidence we would have. And people have figured out that we can use this statistic, the mean residual mean squared, the residuals squared summed over, which we are trying to minimize, right? These are the residuals, as you remember, the original y values and the predicted values squared, residual squared summed over, divided by n minus 2. This is the residual mean squared, and this we can use as an estimate of noise in our data. The lower this value, the less the noise, the more the confidence we will have. There is a kind of shortcut way to calculate the same term that we will also be using also when solving questions. When you solve the questions at the back of the book, you'll also find this. You can find this easy. So this formula, of course, it requires y hat values to be calculated for all the y in the data set, which can be cumbersome, but this formula can be rewritten, can be basically expanded into this form. This is the sum of products for y. Previously, we saw sum of products for x, as you would remember. Here it was sum of products for x. We used as denominator. This is the sum of products for y minus the slope, which we had earlier calculated, sum of products, sum of squares for y, slope, sum of products divided by n minus 2. And the standard error of the slope turns out to be, it's calculated as the mean sum of squares for the residuals, or residual mean squares, what we just saw how to calculate, divided by the sum of squares for x. Okay, so the higher the mean, the residual mean squares, the the higher will be the standard of the slope, and less confidence we will have. Lower this is, lower this will be. Right, and here this is to simply scale the residual mean squares. So this is the standard error, and slopes are supposed to be behaving normally with supposed to be behaving normally, such that if we have an estimate for the slope, we can use the standard error estimate here and critical values from a t-distribution to calculate minimum and maximum level values for beta, the slope estimate. Okay, and the critical values for the t-distribution, we would be using this degrees of freedom n-2. Yeah, so for the line example, we had a slope of 10. We can calculate this one based on just multiplying these and calculating over these elements. You can calculate the residual mean squares and divide by sum of squares for x, take the square root, and there we have our standard error. We can find this critical value of t from the table, and thus we have a range, minimum and maximum range, 95% interval for the slope for beta. And it's pretty positive, so it is pretty outside of zero, as you see. So that suggests that there is a reproducible relationship. Okay, so that was 95% confidence for the slope. Furthermore, we can also calculate the 95% confidence intervals for the response values for each exponential value here for the mean values of the response, basically like the confidence interval for the line here in the middle. Or we can also calculate confidence intervals, again 95% confidence intervals, for the distribution of all the values that correspond to x. So the difference is that in this case, in the confidence bands, let's say we are calculating where we would expect, given the data, and assuming linear relationship, where we would expect the regression curve to pass through. And we expect the curve to pass through as high as this value and as low as this value at x is equal to 0.6. We expect it to be somewhere here. We're not 100% sure, but with 95% probability, it should be here, we say. This is different. Here we are saying at when x is 0.6, where would y values, 95% of y values sit? Here it's where would the mean of y values sit? Here it's about all y values. Where would they sit? As you have noticed in confidence bands, and actually also in prediction intervals, the width is not the same. The narrowest width is where we have most of the data, usually in the middle of the curve. Okay, well, we have more data, standard error will be smaller, and our estimates are more precise. Yeah, prediction intervals are, of course, wider. Yeah, you don't have to memorize formulas again, but you should be able to understand and interpret formulas. So, for instance, here we have the formula for confidence bands. This is what we see here. So how are these bands calculated? They are calculated for each predicted y value. So for each x, we will have a predicted y, right? And the predicted y values will be distributed between this minimum value and this maximum value for each x. For each x, we will have a minimum predicted y and a maximum predicted y. Okay, we can have this range, and this range is defined by the predicted y values here minus and plus the critical value from the t times the standard error of y. And what's the standard error of y? It's the mean residual mean squares. So overall, the sum of squares for the residuals divided by degrees of freedom times this component 1 over n plus the products, the difference between that x value, so we're talking about the single x value, right? So like 0.6. The difference between that x value and the mean of x squared, and here the sum of products, the sum of squares for x, sum of squares for x. So this value is calculated for each x separately. That's why it has different, the confidence bands have different width or height, I mean, however you call it, for different values of x. This numerator term will change as a function of x. Right. So different values for each x. The prediction interval for a single estimate, so where we would expect a single y value, a single male line in this case, to lie. The total range for a single observation to lie within, that's the prediction interval. It's only where the mean would be lying, here where 95% of the whole data would be lying. That's described by this, a very similar formula as you see here. Here, this the same. What only is different is this one here. Compare this formula and this formula. The numerator here is the same, sum of products, 1 over n, but there's also this one. And so the standard errors are much larger. Okay, standard errors are larger. With this one, we'll have larger standards, and these minimum and maximum values will also be large. How these formulas are derived, we won't be learning. Again, we will have different standard error values for each x. For each x, we'll have estimates, best fit for y, and also the standard of the best fit. Yeah, and perhaps we can stop here and we can continue with the extrapolation and other issues in the next part of the lecture.